Good morning, everybody. Here we are discussing about sensors. Here too, we have discussed about position sensors, proximity sensors, displacement sensors, velocity sensors. We have used. Then previous day we have learned about force sensors, pressure sensors, motion sensors. We have here to learn piezoelectric sensors, tactile sensors. Now today we are going to discuss about temperature sensors. So many of you know what is a bimetallic strip. What is a bimetallic strip? Anybody? What is bimetallic strip? What should be the properties of these two metallic strips?
So the temperature. So that means all metallic properties are there, all should be same for the two metallic strips.
No. What is then there? For bimetallic strips, what should be the properties of these two? What should be
Thermal expansion.
Yes, coefficient of thermal expansion or thermal expansion, that should be different. That is why if a strip, whenever they are subjected to same amount of temperature change, the metal strip with higher thermal expansion will elongate longer than the other, that is with lower thermal expansion. So as a result, there will be concavity on the concavity that is being bent like this, concavity on the lower thermal expansion will break and convexity on the higher thermal expansion. So as they are rotating, they may trigger a switch on or like that. So let us see how this works and the details of it. So this is the construction of bimetallic strip. We can see that this is high expansivity material, that is material with higher coefficient of thermal expansion. It is with lower coefficient of thermal expansion. So this is known as bimetallic strip. We can see that there is a soft iron, here is a small magnet, and this is a set temperature adjustment. That is, there could be some graduations. By rotating the screw, we can move this small magnet either this direction or this direction, and actually we can set the temperature. Suppose we are setting the temperature at 80 degrees Celsius. So when it will reach 80 degrees Celsius, there will be a touch. If at higher temperature it is to be touched, then it is to be moved in this direction, so that at more higher temperature it will touch. So these graduations are calibrated against this temperature, and accordingly we can set. Now the question is, why we are giving a small magnet and a soft iron here? What can be the reason? Why this small magnet and soft iron is there? Why this small magnet and soft iron is there? Suppose you want to make it at 80 degrees Celsius. Okay. At 80 degrees Celsius it will touch, and as it will touch, there will be an electrical contact made, and the current will flow. That current may trigger a switch on or off according to your design or your equipment that will be done. Now, as soon as there is touch, suppose it is subjected to some heating element, okay, and the heater will be off. Okay, you want to maintain the temperature of a particular place. Suppose a furnace you want to maintain the temperature at a particular temperature, say 80 degrees Celsius. For time being, we are saying that 80 degrees Celsius. So at 80 degrees Celsius it is touching, and as soon as it is touching, the heater will be off. Okay, something will be there so that the heater will be off, and as a result temperature will drop down. So it will the thing is that, so whenever there will be a touch, an electrical contact will be made, and as a result something will happen. So if this now small magnet and soft iron is there, so suppose at that particular temperature it is making the contact and heater is off, and temperature is decreasing, but due to this soft iron and small magnet, they will not detach immediately. Say that is intentionally we are providing some hysteresis, so that at some lower temperature it will, the switch or this contact will be broken. This contact will be open. Say at 5 degrees or 10 degree lower, according to our design and the strength of this small magnet and soft iron, this will be there. Are you getting the point?
Yes.
Very good. Next is resistance temperature detectors. In short, we say these RTDs. RTDs work on the principle that electrical resistance in general increases with temperature. Isn't it?
Yes, sir.
Electrical resistance increases with temperature. So, what is the reason behind this? What is the reason behind that increase of temperature with increase of resistance with temperature of some conductors, say especially metal conductors? What is the reason? Yeah, there. We are heating up, temperature is increasing, but why resistance is decreasing? What is the cause of resistance?
Sir, electrons
No.
restriction on the source electron.
How this restriction is there? Electrons, you know the electron cloud theory of metallic conductors, that in that electrons are assumed to be as a cloud, because the electrons are freely can move within the metal. Okay, so as they can freely move, so there should be no resistance, but there are resistances.
Yes.
Why is resistance? Due to the internal kinetic energy. Actually, the temperature is a measure of, or is a reflection of, or is a function of, you can say, internal kinetic energy. Internal kinetic energy consisting of internal translational energy, internal rotational energy, internal vibrational energy. Say for a solid substance, metal, there will be internal vibrations, and as temperature increases means what? Internal kinetic energy is increasing. That is, this vibration is increasing. As this vibration or this movement is increasing, they are restricting the flow of electrons. Okay, so resistivity is increasing. So that is the reason. Now that can be utilized for measurement of temperature. Let us see how. So in general, it is given by this formula that R0 or R0, you can say, is the resistance at say 0 temperature, or we are taking a particular temperature to be 0 temperature, say 10 degree, 0 degree Celsius, you can take 100 degrees Celsius, according to our convenience we can take. So at that temperature, what was the resistance? And alpha is the coefficient of thermal expansion. Coefficient of temperature resistance. Okay, so that is per degree to increase 1 degree Celsius or 1 degree Fahrenheit, whatever, 1 degree temperature if increase, then what is the change in resistance? That is denoted by alpha. So and T is the temperature at which RT we are finding. So in general, that linear relationships. Many metals show this linear relationship, but all the metals do not show this. Say for copper, to some extent it is linear and it is becoming non-linear. Some metals are there, like nickel, there will be two different kind of alpha, coefficient of resistance of temperature. So up to this temperature, one coefficient, after that another coefficient. Here the coefficient was higher, here the lower. We can see as the slope is lower here the slope is higher. And some metals are there, say platinum. For most of the temperature range, we can see that it is linear. Okay, so these RTDs can be connected with one of the arms of a piston bridge, and other piston bridge are initially balanced. Now as the temperature is increasing, the resistance is increasing. Okay, so there is out of balance voltage in the Western bridge can be calibrated against this temperature change. Fine. So by that we can measure the temperature. So RTDs, and they can measure somewhat higher degrees of temperature or higher range. So this we have already explained and discussed. Okay, how this is connected, you can see. So these are the connecting leads. These are the resistance thermometer. That is, these RTDs are there here, and this is connected to the Western bridge. You can see these are on the Western bridge. Others are balanced, and this out of balance voltage in the Western bridge can be calibrated against the temperature change here. So we can measure the temperature easily. Fine. Now there are some applications of these resistant temperature detectors: air conditioning and refrigeration servicing, food processing, stoves and grills, textile production, plastic processing, petrochemical processing, microelectronics, air, gas and liquid temperature measurement in pipes and tanks, exhaust gas temperature measurement. So we can see that many industrial applications are there for these resistant temperature detectors and RTDs. So very important sensor, we can say. Now thermistors. These are some semiconductor device. Thermistors, you know, there are some diodes and transistors. In case of diodes and transistors, what happens with temperature change? You can recall, try to recall. In case of diodes and transistors, what happens with the resistance with temperature? Anybody? Diagram তুমি আরো ভালো বুঝতে পারবে, বলার চেষ্টা করো। In case of diodes and transistors, what happens with temperature? There, mobility of the charges increases with temperature. Here the theory is different. In case of metals, there was electron, cloud, electron, etc. But here the thing is different. As the temperature increases, mobility of charges increases. Okay, diffusion region decreases. As a result, what will happen? Amount of current will increase. Amount of current is increasing, which we can say the resistance is decreasing. However, in that case, the change in resistance with temperature is somewhat exponentially changes. So let us see how these can be used as sensors. Thermistors follow the principle of decrease in resistance with increasing temperature. The material used in thermistors are generally semiconductor materials such as filtered metal oxide. That is mixture of metal oxide, chromium, like chromium, cobalt, iron, manganese and nickel, or doped polycrystalline ceramic containing barium titanate and other compounds. So these become some semiconducting materials. As the temperature of semiconductor material increases, the number of electrons able to move about increase, which results in more current in the materials and reduced resistance. So amount of charge carriers, number of charge carriers increases with temperature. More number of electrons comes to the conduction band, we can say. That is, as you are giving more and more temperature, the electrons in the valence band getting more and more energy. So more and more electrons can be in the conduction band, and as a result, what happens? Available free charge carriers increases. In case of N-type electrons, in case of P-type, number of holes increases. So as a result, resistance is decreased. And another important aspect of thermistors are that we can practically measure the temperature of a point, because this is in the shape of a say spherical cylindrical shape, but this is in the shape of that much. So say 1 millimeter. Okay, with this radius, say diameter of 1 millimeter. So very small bulb you can make, and at that point this thermistor will be there, and that can be connected like this. So that is one advantage. Suppose you are doing some experiments to measure the temperature at various points on a cutting tool. You are doing machining operations, and you are performing some experiment that how temperature is generated at different points of the tool. Accordingly, some decision can be taken for like that. So on the face at different points, on the red surface of the tool at different points, you need to find the temperature, or the flank surface. Okay, so these at different points, as you want to find the temperature at different points, you can attach these sensors by making some holes. However, thermocouples can also be used and has been used. If you go to the literature, the journal papers, you can see that there are use of these thermocouples to measure this temperature. There are other methods also, say infrared measurement, etc. So you can see that this is the kind of bead. So thermistors are available in the form of bead as this, or press this, probe or chip. Figure shows the construction of a bead type thermistors. It has a small bead of dimension from 0.5 mm to 5 mm, coated with ceramic or glass material. The bead is connected to an electric circuit through two links. You can see to protect from the environment, and leads are contained in a stainless steel tube. And for say thermodiodes, so this is the relations of temperature, resistance with temperature. RT is equal to A into beta by T. Okay, that is the temperature. The exponential, there is some mistake. There should be negative quantity. It is decreasing. Okay. Now, the resistance of conventional metal oxide thermistors decreases in a very non-linear manner with an increasing temperature. So it has negative temperature coefficients, NTCs. Positive temperature coefficients thermistors are available. The change in resistance per degree change in temperature is considered to be larger than that which occurs with metals. The resistance temperature relationship for thermistors can be described by equation RT A to the power minus B by beta. There should be minus. Where RT is the resistance temperature T, A and B being the constants. A and B are the constants. Some other points are thermistors have many advantages when compared with other temperature sensors. They are rugged. Rugged means
any temperature, any environmental condition.
Yes, very. They can be very small, so enabling temperature to monitor at virtually at a point. Because of their small size, they respond very rapidly with changing temperature.
Yes.
So very dynamic temperature can be measured with these. They give very large changes in resistance per degree change in temperature. That means they have very high sensitivity. Okay, and high resolution also. Their main disadvantage is they are non-linear. Thermistors are used with electronic systems for cars to monitor such variables as air temperature and coolant air temperature. So one application you can see. There are other applications also, industrial applications. To monitor the coolant temperature and the oil temperature inside the engine. To monitor the temperature of an incubator. You know what is an incubator? Where eggs are hatched. What is it? Thermistors are used in modern digital thermostats. Modern digital thermostats do not use that metal systems. To monitor the temperature of battery packs while charging. To monitor temperature of hot ends of 3D printers. To maintain correct temperature in the food handling and processing industry equipments. And to control the operation of consumer appliances such as toasters, coffee makers, refrigerators, freezers, etc. So you can see there are various or many important industrial applications with these thermistors. Now, thermodiodes and transistors. A junction semiconductor diode is widely used as a temperature sensor. When the temperature of doped semiconductor changes, the mobility of the charge carrier changes, and this affects the rate at which electrons and holes can diffuse across p-n junction. Thus, when p-n junction has a potential difference V across it, the current I through the junction is a function of the temperature. So I is I naught equal to dV by kT minus 1, where this T is the temperature at Kelvin scale, is the charge, and K and I naught are constants. K is Boltzmann constant. However, this is one nonlinear relationship. If we, instead of current, if we take the voltage as a output, then somehow we can make that relationship with voltage and temperature to be linear. So if we take logarithm on both sides, so I by I naught minus 1 is equal to usual dV by kT. On that equation, you take logarithms on both sides, and we can find this relationship. So V is equal to kT by P, then I by I naught plus 1. Now, if I remains constant, if we keep the I constants, we can see V is proportional to the temperature. Okay, so in this way we can make that sensor to be a linear sensor. Thus, for a constant current, we have V proportional to temperature and take on the Kelvin scale, and so a measurement of potential difference across the diodes at constant current can be used as a measure of the temperature. Such a sensor is compact like thermistor, but has a great advantage of giving a response which is a linear function of temperature. Diodes for use as temperature sensors together with the necessary signal conditioning are supplied as integrated circuits LM3911 and give a very small compact sensor. The output voltage of LM3911 is proportional to the temperature at the rate of 10 millivolt per degree Celsius. And thermodiodes and thermotransistors. In the same manner, we can use also thermotransistors. So, in a similar manner, the as to the thermodiodes, for thermistors, the voltage across the junction between the base and the emitter. Base and the emitter depends on the temperature and can be used as measure of temperature. A common method is to use two transistors with different collector currents and determine the difference in the base emitter voltage between them. This difference being directly proportional to the temperature of the Kelvin scale. Such a transistors can be combined with other circuit components on a single chip to give a temperature sensor with its associated signal conditioning. So we have already discussed in our initial classes or initial discussions of temperature and transducers. We stated that there is a subtle difference between transistor and sensors. Can you recall it? What is the difference between a transistor and a sensor? What is the difference between? You should remember. What is the difference between a transistor and a sensor? What is transistor itself? You know, anybody of you know what is transistor? What is transistor? Transistor. Yes? Okay. A transistor is a device which can convert one form of energy or signal to another form of energy or signal. Suppose the thermocouple is a transistor. All these thermodiodes, thermotransistors, they are also transistors, because changing temperature or temperature signal is being converted into changing voltage, some electrical quantity, voltage or current, isn't it? So that is transducer. But for a very small output in the range of say millivolt or microvolt, that is to be amplified very input. So we need amplifiers. Sometimes we use filters so that some noise frequencies can be eliminated. Okay, some filters we can use. In case of digital converter, can be used in digital circuits or digital devices, or even a digital signal that can be might be needed to be converted into analog signal. So digital to analog converter might be needed. So these are known as signal conditioning devices. So a transducer along with some these kind of signal conditioning devices is known as sensor. From the market we buy the sensor, means it is having that required for this circuit along with the signal conditioning devices. Okay, not only they will have the transducer, but whenever you are buying some sensor, that means you are buying the sensor integrated with the signal conditioning devices. Only then it will work. Okay, you can work directly for your microcontroller applications. Right? So that is being stated here that the temperature sensor with associated signal conditioning device, and that temperature sensor is known as for a thermo transistor LM35. This sensor can be used in the range of -40 to 100 degrees Celsius and gives an output of 10 millivolt per degree Celsius. Is that understood?
Yes.
Any queries from this? Up to this? Any queries? Anybody? Now thermocouple. I guess all of you know what is Seebeck effect. What is Seebeck effect? You know? Can anybody explain what is Seebeck effect? Seebeck effect. Anybody of you tell me what is Seebeck effect? Can anybody recall? Can you remember that two metals will be there and two junctions will be there, and one junction is kept at say one temperature, say at 0 degrees Celsius or something temperature, and other junction at different temperatures. Can you recall this? And as a result, what will happen? Two different metals are there. They are connected at two different and two junctions are being formed, and these two junctions are kept at different temperatures. Then what will happen? An EMF will be generated. Okay, that effect is known as Seebeck effect. Now this and there will be, so that EMF generated, you can say, or EMF is being produced there, and that EMF is a function of temperature. Although there is a parabolic function, there will be two constants related with these two metals, and some parabolic equations are there. However, the main thing is that we can measure the temperature. So if we keep one junction, say cold junction at a particular temperature, so the standard temperature is 0 degrees Celsius, and other junction is kept at different temperature. That is, we take at that point of which we want to measure the temperature. Okay, at the point or object of which we want to measure the temperature. So that EMF induced can be calibrated against this temperature at the hot junction. Okay, and that can be used as temperature measure. Here also this thermocouple is a transducer, and the EMF generated is very low range, say in the millivolt. So to have proper use of it, we need an amplifier. So some signal conditioning device will be needed, and we can go to the thermocouple sensor. Right? So let us again see what is thermocouple. Thermocouples works on the fact that when a junction of dissimilar metals heated, it produces an electric potential related to temperature as per Thomas Seebeck 1820. When two wires composed of dissimilar metals are joined at both ends and one of the ends is heated, then there is a continuous current which flows in the electric circuit. The net open circuit voltage, that is known as the Seebeck voltage, is a function of the junction temperature and this is the construction. How this can be, you can see metal A and metal B has kept, these junction are kept at a particular temperature, and hot junction is at the heat source, and there is a compensation circuit is needed for temperature compensation, and there will be some signal conditioning devices and a circuitry where we can display the temperature, or that can be used in some processor. So that the EMF generated or potential difference generated can be expressed by AB plus BD square. A and B are the constants related with the two metals, and T is the temperature at which we want to measure. We are getting this potential difference, and we can see that this is the parabolic equation. Okay. So, if two different metals are joined together, a potential difference occurs across the junction. That the potential difference depends on the metals used and the temperature of the junction. A thermocouple is a complete circuit involving two such junctions. If both junctions are at the same temperature, there is no net EMF. If, however, there is a difference in the temperature between the two junctions, there is an EMF. The value of this EMF E depends on the two metals, that is this A and B, constant, and the temperature T of the both the junction. Usually one junction is held at 0 degrees Celsius, and then to a reasonable extent a foreign relationship holds in most of the cases. Okay. And we can see for different pairs of metal junctions what can be the EMF generated at different for different metal combinations. So you can see in the graph these letters B, J, these were there. Now B is platinum 30%, platinum 30% rhodium, and platinum with 6% rhodium. You can see the range is very high, and per degree Celsius, that is in the microvolt range. You can see. Okay, so this must have to be amplified. Otherwise, we cannot measure sensitive temperatures. Okay. Is chromium constant at -200 to 1000. For iron constant at their range is -200 to 900 degrees Celsius. For kerosene, for chromium at alumel is a alloy, -200 to 1300 degrees Celsius. Kerosene and nisin, all these are alloys. You can see -200 to 1300 degrees Celsius. Platinum with 13% rhodium is 0 to 1400. Platinum with 10% rhodium 0 to 1400 degrees Celsius. And copper and constant. And you can see maximum sensitivity is occurring with these chromium constant, isn't it? Maximum sensitivity. We can this you can say as sensitivity. What is the output with input changing input per degree per unit changing? What is the output per unit changing input? That is the sensitivity. So you can see the sensitivity is highest for this chromium constant. Then iron constant is there. This is also having chromium and fire, and this also copper constant. Fine. Yes. So what are the different applications of thermocouplers? To monitor temperatures and chemistry throughout the steel making process. You know these thermocouples. Have you worked with heat treatment processes or heat treatment furnace? Or have you any knowledge of these heat treatment furnaces? Yes. Yeah.
Yes, sir.
Bolo. Then. So, what is the use of this heat treatment furnace?
Heat furnace basically used for metal already been produced. Then if we want to increase or decrease some metallic properties, then we cannot remelt the metal and reproduce the metal. Then we can add like different temperatures. We can basically have a
change the microstructure. Through heat treatment, we change the microstructure. Suppose a particular metal, say suppose ferrous, say iron, say low carbon iron, is heated to its austenitic temperature, then it is quenched in water. So rapid cooling is there. As a result, what will form andesite, and this soft alloy or metal will become very much hard, isn't it? Through andesite process. Now, it is hard or through other process. Suppose you have some, but the same composition, same material can have different properties with different your temperature. So you can heat it again to a particular temperature, austenitic things. Now, after that, how you are cooling? You are cooling in water, cooling in air, you know that will normalization, or cooling in the furnace. You are switching off the furnace. As the furnace cools down, automatically furnace is insulated, you know, so it will take a very high time, long time to cool down, and there will be another. So that is, you know, annealing. Even this annealing can be of various types. To which temperature it is taken? Now another is that there are different tempering processes. In tempering processes, what happens? You are heating that so to some say a particular temperature below lower critical temperature or higher critical temperature. You are taking it to higher critical temperature. Then you are lowering down at a particular temperature and keeping that temperature constant for some time. And then again you are cooling. So at what temperature you are keeping that constant? For a long time you are keeping that temperature constant. So depending on the temperature, different microstructures can be formed. Sorbite, spheroidite, and different such microstructures can be formed, and as a result, different properties can be achieved. Okay, their hardness properties means mechanical properties: hardness, toughness, ductility, strength, okay, variability. So these properties can be changed with this changing microstructure. So in these kind of metal furnaces, suppose you are maintaining the temperature. First of all, you need to know the temperature, and the temperature is also to be maintained. So in many cases, these thermocouples are used for measurement of this. Okay, so accordingly you can control. Okay, depending on your program, you can control. So in case of that is one applications. Other applications are testing temperatures associated with processes with process plants, as for example chemical production and petroleum refineries, testing of heating appliances and safety, temperature profiling in ovens, furnaces and fuels, temperature measurement of gas turbine and engine exhaust, monitoring of temperature throughout the production of smelting process industry, iron and aluminium industry. So very important applications of this thermocouple with respect to metal processing or metal making industry or steel making industry, steel smelting shop. You know the blast furnace is there. Other such kind furnaces will be there. On those furnaces also temperature is to be maintained and temperature is to be monitored and accordingly or controlled. Isn't it? Yes. And then only you can have your desired properties or desired things involved. Light sensor. A light sensor is a device that is used to detect light. There are different types of light sensors such as photocells and photoresistors. We have already discussed about these photodiodes. That whenever light falls on it, there will be current. It is connected in reverse junction, and whenever light falls on it, depletion region is annihilated and current can pass through it. And so these can be used as detector of light. Okay, so that is our discussion. So how this works, these photoresistors you can see. We have already explained this in our previous clip. So you can see there is a ceramic substrate, two electrodes are there, and these are the lead wires. There is a resin encapsulation, and these are the conducting resin. figure is a construction of a photoresistor. The series resistor coil is mounted on a ceramic substrate. This assembly is encapsulated by resin material. The sensitive coil electrodes are connected to the control system through lead wires. On incidence of high intensity light on the electrodes, the resistance of resistor coil decreases, which will be used further to generate the appropriate signal by the microprocessor via lead wires. Photoresistors are used in science and in almost any branch of industry for control, safety, amusement, sound reproduction, instruction, and measurement. Computers, wireless phones, and televisions use ambient light sensors to automatically control the brightness of the screen. Barcode scanners used in trailer locations work using light sensor technology. So you can see you have seen all these things, and what is the sensor behind it, now you can know. In space and robotics, for controlled and guided motions of vehicles and robots, listen carefully, these are very important applications. In future, you might be designing some of these. So, in space and robotics, the controlled and guided motions of vehicles and robots, the light sensor enables the robot to detect light. Robots can be programmed to have a specific reaction if a certain amount of light is detected. Auto flash for camera, you are using this, and industrial process control. So, photodiode we have already discussed how this works, and similar to this photoresistors, the photodiode applications are similar things. You can see there are applications on camera, medical, in medical CT scanner, X-ray detection, pulse oximeters, blood particles analyzer, in industry barcode scanners, light pens, brightness control, encoders, position sensors, surveying instruments, copiers, density. In copiers, what should be the density of toners at different positions, different points, that will be controlled by this photodiode. Safety equipment, smoke detectors, flame monitors, security inspection equipment, like airport X-ray, intruder alert. Then in automotive industry, headlight, dimmer, twilight detectors, climate control, the sunlight detector, and communication, fiber optic links, optical communications, optical remote control. So you can see how important applications are there. So with this we are concluding our today's class, and in the next day what should we start? There are two options. One, we can start our control engineering. Another, we can start with our say electrical actuators or actuators. Mechanical actuators should be there, electrical actuators should be there, and pneumatic and hydraulic actuators should be there. So what should we start first? What will be comfortable? I guess many of you know the electrical actuators. Motors we have studied, some of you, isn't it?
Yes.
Okay, so and control engineering will be newer to you. So I will first start our control engineering. Okay, the basic concepts regarding this control engineering is very much required, because for designing of any mechatronic system, the control is must, and that is the heart or brain of the system, you can say. So we will start with that.
Yes.
Okay, so for the time being, okay, bye.